Hello everyone. So far in this series on data structures, we have talked about some of the linear data structures like array, linked list, stack, and queue. In all these structures, data is arranged in a linear or sequential manner, so we can call them linear data structures. And we have also talked about tree, which is a non-linear data structure. Tree is a hierarchical structure. Now, as we understand, data structures are ways to store and organize data, and for different kinds of data we use different kinds of data structures. In this lesson we are going to introduce you to another non-linear data structure that has got its application in a wide number of scenarios in computer science. It is used to model and represent a variety of systems, and this data structure is graph. When we study data structures, we often first study them as mathematical or logical models. Here also, we will first study graph as a mathematical or logical model, and we will go into implementation details later. Okay, so let's get started. A graph, just like a tree, is a collection of objects or entities that we call nodes or vertices connected to each other through a set of edges. But in a tree, connections are bound to be in a certain way. In a tree, there are rules dictating the connection among the nodes. In a tree with n nodes, we must have exactly n minus 1 edges. One edge for each parent-child relationship. As we know, an edge in a tree is for a parent-child relationship, and all nodes in a tree except the root node would have exactly one parent. And that's why if there are n nodes, there must be exactly n minus 1 edges. In a tree, all nodes must be reachable from the root, and there must be exactly one possible path from root to a node. Now in a graph, there are no rules dictating the connection among the nodes. A graph contains a set of nodes and a set of edges, and edges can be connecting nodes in any possible way. Tree is only a special kind of graph. Now, graph as a concept has been studied extensively in mathematics. If you have taken a course on discrete mathematics, then you must be knowing about graphs already. In computer science, we basically study and implement the same concept of graph from mathematics. The study of graphs is often referred to as mathematical terms. We can define graph something like this. A graph G is an ordered pair of a set V of vertices and a set E of edges. Now I'm using some mathematical jargon here. An ordered pair is just a pair of mathematical objects in which the order of objects in the pair matters. This is how we write and represent an ordered pair. Objects separated by comma put within parentheses. Now because the order here matters, we can say that V is the first object in the pair and E is the second object. An ordered pair AB is not equal to BA unless A and B are equal. In our definition of graph here, first object in the pair must always be a set of vertices and the second object must be a set of edges. That's why we are calling the pair an ordered pair. We also have concept of unordered pair. An unordered pair is simply a set of two elements. Order is not important here. We write an unordered pair using curly brackets or braces. Because the order is not important here, unordered pair AB is equal to BA. It doesn't matter which object is first and which object is second. Okay, coming back. So a graph is an ordered pair of a set of vertices and a set of edges, and G equal VE is a formal mathematical notation that we use to define a graph. Now I have a graph drawn here in the right. This graph has 8 vertices and 10 edges. What I want to do is I want to give some names to these vertices, because each node in a graph must have some identification. It can be a name or it can be an index. I'm naming these vertices as V1, V2, V3, V4, V5 and so on, and this naming is not indicative of any order. There is no first, second and third node here. I could give any name to any node. So my set of vertices here is this. We have 8 elements in the set: V1, V2, V3, V4, V5, V6, V7 and V8. So this is my set of vertices for this graph. Now what's my set of edges? To answer this, we first need to know how to represent an edge. An edge is uniquely identified by its two endpoints. So we can just write the names of the two endpoints of an edge as a pair, and it can be a representation for the edge. But edges can be of two types. We can have a directed edge in which connection is one way, or we can have an undirected edge in which connection is two-way. In this example graph that I'm showing here, edges are undirected. But if you remember the tree that I had shown earlier, then we had directed edges in that tree. With this directed edge that I'm showing you here, we are saying that there is a link or path from vertex U to V, but we cannot assume a path from V to U. This connection is one way. For a directed edge, one of the endpoints would be the origin and the other endpoint would be the destination. And we draw the edge with an arrowhead pointing towards the destination. For our edge here, origin is U and destination is V. A directed edge can be represented as an ordered pair. First element in the pair can be the origin and second element can be the destination. So with this directed edge represented as ordered pair UV, we have a path from U to V. If we want a path from V to U, we need to draw another directed edge here with V as origin and U as destination. And this edge can be represented as ordered pair VU. The upper one here is UV and the below one is VU. And they are not same. Now if the edge is undirected, the connection is two-way. An undirected edge can be represented as an unordered pair. Here, because the edge is bidirectional, origin and destination are not fixed. We only need to know what two endpoints are being connected by the edge. So now that we know how to represent edges, we can write the set of edges for this example graph here. We have an undirected edge between V1 and V2. Then we have one between V1 and V3. Then we have V1, V4. This is really simple. I'll just go ahead and write all of them. So this is my set of edges. Typically in a graph, all edges would either be directed or undirected. It's possible for a graph to have both directed and undirected edges, but we are not going to study such graphs. We are only going to study graphs in which all edges would either be directed or undirected. A graph with all directed edges is called a directed graph or digraph, and a graph with all undirected edges is called an undirected graph. There is no special name for it. Usually, if the graph is directed, we explicitly say that it's a directed graph or digraph. So these are two types of graph: directed graph or digraph in which edges are unidirectional or ordered pairs, and undirected graph in which edges are bidirectional or unordered pairs. Now, many real-world systems and problems can be modeled using a graph. Graphs can be used to represent any collection of objects having some kind of pairwise relationship. Let's have a look at some of the interesting examples. A social network like Facebook can be represented as an undirected graph. A user would be a node in the graph, and if two users are friends, there would be an edge connecting them. A real social network would have millions and billions of nodes. I can show only few in my diagram here because I'm short of space. Now, social network is an undirected graph because friendship is a mutual relationship. If I'm your friend, you are my friend too. So connections have to be two-way. Now, once a system is modeled as a graph, a lot of problems can easily be solved by applying standard algorithms in graph theory. Like here in this social network, let's say we want to do something like suggest friends to a user. Let's say we want to suggest some connections to Rama. One possible approach to do so can be suggesting friends of friends who are not connected already. Rama has three friends: Ella, Bob, and Katie, and friends of these three that are not connected to Rama already can be suggested. There is no friend of Ella which is not connected to Rama already. Bob, however, has three friends, Tom, Sam, and Lee, that are not friends with Rama, so they can be suggested. And Katie has two friends, Lee and Swati, that are not connected to Rama. We have counted Lee already, so in all we can suggest these four users to Rama. Now, even though we described this problem in context of a social network, this is a standard graph problem. The problem here in pure graph terms is finding all nodes having length of shortest path from a given node equal to 2. Standard algorithms can be applied to solve this problem. We'll talk about concepts like path in a graph in some time. For now, just know that the problem that we just described in context of a social network is a standard graph problem. Okay, so a social network like Facebook is an undirected graph. Now let's have a look at another example. Interlinked web pages on the internet or the World Wide Web can be represented as a directed graph. A web page that would have a unique address or URL would be a node in the graph, and we can have a directed edge if a page contains link to another page. Now once again, there are billions of pages on the web, but I can show only few here. The edges in this graph are directed because the relationship is not mutual this time. If page A has a link to page B, then it's not necessary that page B will also have a link to page A. Let's say one of the pages on mycodeschool.com has a tutorial on graph, and on this page I have put a link to Wikipedia article on graph. Let's assume that in this example graph that I'm showing you here, page P is my mycodeschool tutorial on graph with this address or URL mycodeschool.com/videos/graph. And let's say page Q is the Wikipedia article on graph with this URL wikipedia.org/wiki/graph. Now on my page, that is page P, I have put a link to Wikipedia on page P. You can click on this link and go to page Q. But Wikipedia has not reciprocated to my favor by putting a link back to my page. So if you are on page Q, you cannot click on a link and come to page P. Connection here is one way. And that's why we have drawn a directed edge here. Okay, now once again, if we are able to represent web as a directed graph, we can apply standard graph theory algorithms to solve problems and perform tasks. One of the tasks that search engines like Google perform very regularly is web crawling. Search engines use a program called web crawler that systematically browses the World Wide Web to collect and store data about web pages. Search engines can then use this data to provide quick and accurate results against search queries. Now, even though in this context we are using a nice and heavy term like web crawling is basically graph traversal, or in simpler words, act of visiting all nodes in a graph. And no prizes for guessing that there are standard algorithms for graph traversal. We'll be studying graph traversal algorithms in later lessons. Okay, now the next thing that I want to talk about is concept of a weighted graph. Sometimes in a graph, all connections cannot be treated as equal. Some connections can be preferable to others. Like for example, we can represent intercity road network, that is the network of highways and freeways between cities, as an undirected graph. I'm assuming that all highways would be bidirectional. Intracity road network, that is road network within a city, would definitely have one-way roads, and so intracity road network must be represented as a directed graph, but intercity road network in my opinion can be represented as an undirected graph. Now clearly we cannot treat all connections as equal here. Roads would be of different lengths, and to perform a lot of tasks, to solve a lot of problems, we need to take length of roads into account. In such cases, we associate some weight or cost with every edge. We label the edges with their weight, length of the roads. In this case, so what I'll do here is I'll just label these edges with some values for their lengths. And let's say these values are in kilometers. And now edges in this graph are weighted, and this graph can be called a weighted graph. Let's say in this graph we want to pick the best route from city A to city D. Have a look at these 4 possible routes. I'm showing them in different colors. Now if I would treat all edges as equal, then I would say that the green route through B and C and the red route through E and F are equally good. Both these paths have 3 edges. And this yellow route through E is the best because we have only 2 edges in this path. But with different weights assigned to the connections, I need to add up weights of edges in a path to calculate total cost. When I'm taking weight into account, shortest route is through B and C. Connections have different weights, and this is really important here in this graph. Actually, we can look at all the graphs as weighted graphs. An unweighted graph can basically be seen as a weighted graph in which weight of all the edges is same, and typically we assume the weight as 1. Okay, so we have represented intercity road network as a weighted undirected graph. Social network was an unweighted undirected graph, and World Wide Web was an unweighted directed graph, and this one is a weighted undirected graph. Now this was intercity road network. I think intracity road network, that is road network within a city, can be modeled as a weighted directed graph, because in a city there would be some one-ways. Intersections in intracity road network would be nodes, and road segments would be our edges. And by the way, we can also draw an undirected graph as directed. It's just that for each undirected edge, we'll have two directed edges. We may not be able to redraw a directed graph as undirected, but we can always redraw an undirected graph as directed. Okay, I'll stop here now. This much is good for an introductory lesson. In next lesson, we'll talk about some more properties of graph. This is it for this lesson. Thanks for watching.